Hello everyone, welcome to live Brum.ai. I'm going to start off by thanking Atlas for the comparison. Thank him for his divine intervention of having this on a Thursday and not Monday and Tuesday. I'm sure we've all been a little sweat on the floor. Today we've got three speakers. We've got Thomas, who's going to be our first speaker. He's going to talk to us about AutoML. And then we've got some short lightning round speakers following that as well. So it's good to see some new faces, some faces that have not been very long time. Again, for the old familiars, for the ones that were here last time, it's good to see you all again. So without further ado, I'll introduce our first speaker. We have Thomas. He is from AutoML. He's based in Portland, Oregon. So we've flown in a long way away through Zoom to get him here, and he's going to be talking to us about Modela AI, which is a AutoML platform that uses Kubernetes. So without further ado, Thomas, you can share your screen, please.
Hey, Thomas, you okay to start sharing?
Okay, we can start looking at Talus's nose. You should also mute that microphone.
And you're muted in Zoom as well.
Hello? You see me? Are we good?
Yeah, that's pretty good. Thank you.
Can I start?
Yeah.
Okay. Okay, I'm going to start the presentation. Okay, so first of all, thank you for having us. Okay, so my name is Thomas Sagi. I'm the founder, co-developer of Modela.ai, which is automatic machine learning on Kubernetes. Okay, so the first thing that I'm going to cover, so basically, so just a background around me, I am a software engineer, developer, and a data scientist. I have multiple degrees, and this has been my project for the last 4 years, and hopefully you find it useful. So what I'm going to explain in the presentation, there is some math, because I want to give you the foundational knowledge in Bayesian optimization and in Kubernetes itself, the architecture. The product is not a Kubernetes, it's not running on Kubernetes, it's basically running in Kubernetes. So it's extension of Kubernetes. So it's going to be very important to understand how Kubernetes work inside in order to understand what the product does. Okay, so the first thing I'm going to describe, I'll give you like general knowledge. Basically, if we look at the machine learning process or that data science process, we start from business understanding. So basically, the first thing that we do is we want to define the data science problem, define the business KPI, what is the success. Then we collect our data, we do some EDA, we then prepare the data, which means the data cleaning, feature selection, etc. Then come the modeling part, which means we need to select a machine learning algorithm, do some hyperparameter optimization manually or grid search, etc. During that, we evaluate our model, select the best one, and put them in production, which means that we package it, for example, in Docker container, put it in a cloud or on Kubernetes, and we need to monitor it for data drift and target drift. So this is the core process. So the question is, what do we want to automate? The answer is, of course, everything. This is the vision of a complete AutoML. But currently, what AutoML that you're going to see in research or in academia is about hyperparameter optimization. So this is mainly the modeling part. So what is hyperparameter optimization? Mainly, maybe you know about it, but again, this is maybe a basic knowledge. What we have is we have this black box function. The problem with hyperparameter optimization is that we have a lot of hyperparameters, and also there is a condition between them. So, for example, if we select a deep learning network, hyperparameters can be our activation function or unit per layer. Or if we select, for example, XGBoost, hyperparameters can be tree depth or learning rate. So the problem is that we don't see our optimization function. What we see is just this black box that we can give it configuration and we get the answer like, some sort of error or error function score. And we want to optimize this function. Another issue is that evaluating the black box is very expensive, can be very expensive. So for example, you want to train deep neural networks, either cost or time, and so we have a budget. So the traditional way to do hyperparameter optimization is either do a grid search or a random search. The problem with grid search is that we have a lot of dimension to optimize. So it's exponential in the number of dimension. And with random searches that we don't use any history. So we waste a lot of time on different points randomly. So the state of the art, there are two ways to do a model search. One is model-based, the other one is model-free. The state of the art in model-based is called sequential model-based optimization. So it's a sequential because we learn from history. So we evaluate the point, evaluate different point in the search space. A model means that we use a surrogate model. In this case, it's going to be the Gaussian processes. And optimization means that we want to optimize. So if you look at Bayesian optimization, we choose the Gaussian processes because we want a regression model that doesn't give us just a point prediction. The Gaussian process model will give us a distribution, a Gaussian distribution prediction for our function. So if we look at this on this picture, on the iteration, we see that we get prediction from the Gaussian process, which are Gaussian, the distribution. We have the mean of the distribution, and this is the real function. In addition, there's something called acquisition function, which basically score the Gaussian process prediction and give us the best point to search next. And the classical acquisition function is the highest expected improvement. So we want basically to search point that will give us the best improvement over all the points that we search until now. Also, we want, there's two phases to the Bayesian search. One is called exploration. The other one is called exploitation. So in exploration, we're basically searching different points in different areas. And in exploitation, we search the point close in the area. And this is usually in the latest iteration of the process. So if we look at the example here, first we make an observation and then we score the points. So we get the acquisition function give us another point. Then in iteration 3, we do the search the optimization, the observation here. Again, we reduce the uncertainty near this point. We get the score from the acquisition function and it decides to exploit. And when it exploits, it gives us another point which it thinks might be the best the best score for this function. And we do that, and we basically, until we reach our budget, where we can optimize the model. So it's much more efficient, like 20, 50x over a random search, or it can get even to a 200x. So it's a very efficient search. So this is the Bayesian optimization. Now, if you, like, there's open source tool called AutoScikit-learn. If you're interested in doing it on your machine or using it in a notebook, the problem is that it is not a distributed search. So it doesn't span machines like Modela. So this is the model-based search. Another way to do a search is called multi-modality search. So in multi-modality search, we use the fact that we can downsample our data or downsample the iteration. So for example, if you use a tree-based model, we can iterate for 10 iterations instead of 50 iterations. So the problem with Bayesian is that in order to find the score, we need to run the model. So for example, we need to train the networks, to the end. With the model-free training, we basically iterate, so we can like allocate our budget. So we start with like smaller model, like smaller data. So for example, we do 9 iteration for 9 points of our resources. We select the best third, and then we increase the modality. So we give the best third and not each one of them 27 iteration, select the best one, and the first one we get 81 iteration. Now, this is a very quick introduction to the subject. There are pitfalls to this model. So there is an algorithm called Hyperband, a company called Determined.ai, which explain how to do it for real-time, but this is just a background to understand what is multimodality. Now, multimodality can also apply, for example, you can train on low resolution images, you can train on part of your data. So this is different modalities. However, we need more automation. So this part is only hyperparameter optimization. What we need is, this is a very, very famous picture, that we have this huge, that like for end-to-end machine learning system, we need the other part. This is a paper from Google. So we want also data verification, and of course we want to manage our serving infrastructure, feature extraction, data collection, monitoring. We basically want to automate. So I'm going to introduce a concept which is the AutoML system, and not just hyperparameter optimization. So an AutoML system, it provides automation behind the scope. So we have automation for data. So for example, we want to automatically recognize data types. We want to automatically do the splitting, like we choose stratified splitting, random splitting, or if you use time series, it's a time split. We want to generate data, data profiling, detect outliers. So this is for data. We want to run data validation. We also want to automatically, even in the training, we want to automatically scale the trainers, handle different hardware, generate reports on the training, automatically generate explanation like sharp p-values, and automatically do distributed training. Like we want to automate this. Basically, we want to automate the CI/CD. We want to move the model between stages, like test stage, and run tests against this model to the stages. We want to automate the monitoring, so we want to do automatic drift detection, automatic logging of prediction, etc. So you get the idea. The idea is that we have the AutoML system, which is a fully AutoML, and there's platform that kind of offering that. Vertex.ai from Google, H2O, DataRobot, and Azure. Kind of it's an end-to-end system, although you need to combine different parts of the product. Now, if we look at automation, so we already have this very popular open source system that is using for data, for application automation and DevOps, and it's already mature with a huge ecosystem, and it's basically Kubernetes. So if we look at Kubernetes, I just want to give, I don't know the level of knowledge of Kubernetes for the audience, so I'm going to start really basic. And if you find it too basic, then I apologize. The idea is that Kubernetes is used for data center automation. It's a project that was started in 2014 based on 10 years of data center automation in Google. It's a very wide industry support at this point. It can be done, it's support on IoT, Edge, private cloud, managed Kubernetes. But the key on Kubernetes, which is not really the container part, is that it's a platform for platform, which means that you can extend it to new domain, okay? Okay, so if you look at Kubernetes, so basically Kubernetes, if you look at it in the philosophical level, it's a database, it's an API database. So everything in Kubernetes is an object. Kubernetes is composed of the control plane, which is the master node, and a data plane, and nodes, which are the worker nodes. And all the objects are stored in this database, the etcd, okay? As you can see, all communication is done via the API server. And all the objects in Kubernetes are declarative in nature. So Kubernetes, you just say what you want. A declarative means that you don't tell Kubernetes what to do. You're just telling what you want, and it will do its stuff, okay? And this is very good for like no code things. You just say, okay, I want the world to look like this, and Kubernetes will do the reconciliation. Now, in order to do this logic, Kubernetes has a bunch of controllers, which I'm going to explain what it is in the future slide, a bunch of controllers and a scheduler to schedule the work. So the scheduler is mainly scheduler jobs, pods, etc. Now, the actual work in Kubernetes is done in the worker node, which is composed from the kubelet. As you can see, the kubelet also connects to the API server. The kubelet is using the watch mechanism, which is very unique to Kubernetes, which means that it gets notified. It doesn't pull the API server. It gets notified when a new object is injected into etcd. And when a new pod needs to run, the kubelet will start the containers on a node. So, but this is just the configuration for the classical Kubernetes. Now, if we go to the terminology, so an object of Kubernetes is a resource. All the resources are declarative, okay? Which means that they have, I'm going to cover a resource in the next slide. Kubernetes comes with a pre-built resource, which you might be familiar with, like the pod, the deployment, and the service. But you can define a custom resource. So the idea behind Modela really is those custom resources. So in Modela, you don't define a model in Python. Actually, you don't use Python at all. You have a model object which contains the definition. So for example, it contains a deep learning architecture, or it contains a scikit-learn pipeline as a Kubernetes API object. And this is the key idea. If you understand this idea, you understand what is Modela. Now, you also don't, and this is where AutoML comes into the picture, you also don't create those models, okay? You just basically submit your data. And Modela will do the rest. So Modela will do this model search that I explained, either Bayesian search, you can choose either Bayesian search or hyperband search, and it will efficiently find the best model for you and do the rest of the AutoML that I've explained. So it's going to deploy the model, etc. So just go back to this slide. So we have the custom resource, which is the model. We define them with the model CRD. And then you have this thing called the controller. So every model, for example, in Modela, every CRD as a controller, which is do the logic in the model. So for example, the model controller will do the training, okay? And there's another concept called an operator, which you might heard of. An operator is basically a controller which has an operational knowledge. So this is mainly used for SRE operation, like backups or upgrade or install. Modela is managed by the Modela operator, which know how to install Modela, watch it, and give you this autonomous design. Okay, so the Kubernetes controller, this is what it does. So basically what the controller do is going to watch for changes in the spec of a new object, perform the logic, and once it reconciled the actual state with the desired state, it's going to update the status. So this is the Kubernetes controller. Now, if we go to Modela, so what is Modela? Modela is a declarative AutoML system, which means that it is based on the strong foundation of Kubernetes. So we get this huge amount of investment, enterprise-ready, code-ready. It's a no-code platform, declarative, and it has around 54, which actually stopped counting, but it has around 54 CRDs in all areas of the data science workflow, like infrastructure. So it manages connection to databases, connection to clouds, connection to other systems, Salesforce, Facebook. The CRD in data, so it does automatic data analysis. And I'm going to go over the QSBM again. I'm going to show you where its CRD fit. It comes with the set of the machine learning controller, which contains the Modela logic. All training is based on AutoML, and it's end-to-end. Okay, it's an AutoML system. So it handles the data, the training, the serving for you. And it doesn't use, most of the code is original. So it doesn't use like other open source products to do its logic. It's written like from scratch. And the Modela operator is in charge of installation and upgrade. So for example, on the right side, we see that the study custom resource. So you can see that you can define like the search, how many models do I need, how to do feature engineering search. So Modela is two-phase search, one for feature engineering, the other one is for the study. You can define the interpretability that you want, okay? So you just give this definition to Modela, and Modela will do the stuff. It generates reports, generate profile, train your model, does a lot of stuff automatically. Okay, so if you look at the Modela system architecture, basically on the master node, we have the Modela, all the logic is in the Modela control plane, which is this. The Modela control plane uses the Modela data plane for optimization and reports. and a lot like report generation, optimization, etc. The Modela UI, there's a Modela frontend written in Vue.js, which is used by the Modela UI. The Modela also comes with a CLI that connects to the Modela API server here. The Modela API server bridge between the Modela clients and the Kubernetes API server. All objects in Modela, because it is Kubernetes based and Kubernetes, we really use the Kubernetes, the etcd to its max. Each object has a time to live. So Modela has this garbage collection. For example, a study can generate 200 models, but most of them you don't really care about. So you're going to garbage collect them into Postgres, which is running inside Modela. Now, another thing is Modela is based, like Snowflake and all the other new design, Modela is stateless. So all the state is stored in a data lake, like here, which can be S3, or it can be MinIO, like if you want to run Modela on-prem. So this is it. And then all Modela jobs are running as a Kubernetes jobs on the worker node. So for example, job for data profiling, job for training, testing, report generation, etc. are native Kubernetes jobs. So Modela use the Kubernetes scheduler for training, etc. So everything is kept inside Kubernetes native with minimal additional code. So this is it. Also, when you want if you put a predictor, which is the prediction server, Modela will gonna use SQLite to store the prediction and to do the drift in the future. It does the drift monitor from this data. So all the prediction are logged into SQLite. Okay. And as a client, Modela, you can either use any standard Kubernetes client like kubectl. Modela comes with a Python SDK, so you can use it from a notebook, and the CLI and the UI, which you're going to see in the demo. Okay, so now I'm going to explain how Modela works for like one model. Okay, so basically, when Modela starts, we have the study controller, and the model controller use the etcd watch mechanism. So they register with the Kubernetes API server. When you submit a study declaratively, the study controller gets notified. It's going to start the HPO session, the hyperparameter optimization session, and it's going to ask for the optimizer for the first model. Okay. Once we get the model, we're going to again call the API server to create the Kubernetes model server. When we get then the model controller, we get notified, and then we create the training job, and it will create a training job. Okay. When the Kubernetes API server creates the job, it's going to create a training job on one of the worker nodes based on the managed image. There's a managed image CRD, so you can have control over the images that running the job. The job itself, the actual trainer is a Python code that converts the Kubernetes model into the actual Python library, so you can convert it to TensorFlow, Keras, or the scikit-learn. It's going to get the data from S3 or from the cluster, going to do the training locally, going to evaluate the model, and it's going to update the Kubernetes API server that the job is done. When this is done, the model controller notified that the job is done. It's going to take all the evaluation metrics like RMSE or any other score, update the model CRD or the model CR. Okay, it's going to update the model CR. It's notified, the API server will notify the study that the model is trained. The study is holding this leaderboard of different models, and it's going to tell the optimizer about the result. The optimizer is going to run this Bayesian optimization or whatever, and come up with the next model. Okay. Okay, so as I said, the Modela CRD are all over the Twist VM, and they support the all data pipeline. I don't have time to go into each one because it's a very big system. And so we can start. So Modela is a multi-tenant base. So anything is under a tenant. A tenant is basically a namespace in Kubernetes. You can define a data product, define your governance and team for a data product. So for example, churn prediction is a data product. All the data handling, the data understanding is done by a data set. And this is basically automatic data handling. So once you submit a data to Modela, which can come from a database, come from the web, from GitHub, or you can upload a CSV file or Excel file. Modela will do validation, profiling, etc. Modela is using the data source for the schema. So every data set in Modela is a data source, which is basically contain the columns and the data tests and validation that you want to do. And everything is also inferred. So in order to create a data source, you just upload your data and Modela infer the data source for you, including the test and the quality check that you want to do. So once we have a data set, we're basically going to create also a report for a data set. The next step is data preparation. I'm not going to go into details here. Basically, Modela is a concept of a data pipeline, and a data pipeline has a different recipe. It's basically a full ETL pipeline with around 230 functions. So we have that, and then once we have the data preparation, once we've done data preparation, the modeling is the modeling part that I described. We have the study CRD, which describes the optimization process, like how many models do you want to run, how many trainers, what kind of algorithms. The actual training is done, it's a two-phase training. So we optimize for feature engineering first. We find the best feature engineering pipeline. And then for that, we find your best model and other parameters based on your task, your data set. So every data set, you can find the optimal model for it. We evaluate based on the task, like different scores, and everything is like assigned back to the model CR. So if you do kubectl described, you're going to see all your scores that you want. And then once you have the model, you can put it in production using the predictor CRD. And this supports like drift detection. It supports shadow modeling, traffic. You can just put like allocate traffic to the models. It does automatic logging. It does a lot of stuff. And then also if you want to give access to a non-data scientist, there's something called a data app CRD, which creates a Streamlit dashboard. It generates a Streamlit dashboard for your predictor. So then you can just give a URL and API key, and everybody can start making prediction. Modela is also support monitoring with the feature histogram CRD. So basically, when you create a data set, you can tell Modela that you want it to be part of the monitoring. Modela actually doing automatically, but you can tell it. So what it does is going to create a feature histogram for each of your features. And then when you're monitoring it, Modela have a live feature histogram you can define it per, like, for example, each hour, okay? And then as soon as, and then each hour, Modela will compare the live histogram with your data set, your training histogram, and compute drift detection parameters. And then it generates an alert CRD, which you can connect it with a notifier CRD to Discord, Slack, etc. So Modela going to give you these alerts that you have a drift. Okay.
Okay.
So now
we're gonna switch screen shares now. So stop screen share. Oh, can you hear me? Oh, can you hear me?
Yeah, we can hear you.
All right, cool. So my name is Liam. I'm the other developer here at Modela, and I'm going to give you a quick demonstration of the platform. First, we're just going to quickly cover how you can install it on your local machine. All you need to do is install a local Kubernetes cluster, which you can do with Docker Desktop or Rancher Desktop. And then all you need to do is run this one command line, and it's going to install the Modela operator, which quickly bootstraps an installation of Modela that's ready to use on your machine. So we're going to go to my local installation of Modela, and this is the tenant dashboard, which contains all of our tenant level resources, which includes our data product and all of our infrastructure resources. Probably the most important resource here is the data product, which is intended to group a single machine learning use case. So you have one set type of default task, your default data location, notification settings, default resources, and so on. So we're going to go to our data product here and start with the data stage, where we're going to upload our data set. But first we need to make a data source, which essentially defines the schema for your incoming data. We need to set the task type, which today we're going to be doing a multi-class with a cars data set to predict the acceptability of a car based on its features. So once we upload our data set, we can send it to the data plane so it can guess all of our columns and its data types. Then we need to select our target variable, which is going to be predicted on. And now that we have our data source, we can create a data set resource, which will be the resource that performs all of the automatic analysis. So all we need to do is upload our data set. And once we submit our resource to the cluster, it's going to start a Kubernetes job, which profiles the data set, runs validation if specified, and so on. So if we go to our jobs tab here, well, for some reason it doesn't show it, but well, eventually it would start a job, but why don't we just go to a completed resource for the sake of time. Once the data set is completed, it would already have generated the profile, which we can view in the profile tab. Yep, so now we'll be able to see all of our data set statistics, our data types, a histogram for each column, which shows the distribution of classes, and also quite a few visualizations that will produce based on the type of data sets, its columns, and so on. And if you wanted to share this profile with somebody else, Modela also automatically generates a report, which we can download and view right here. So it's just a simple PDF report that has all of our visualizations, and you can share with somebody else and so on. So now that we have a completed data set ready to use, we can now put it into the study custom resource. And this is the resource which performs the automatic model search. So our data set is already specified. We just need to select the objective metric, which is how models we train are going to be evaluated. Let's set our training parameters. We can set the amount of resources which will be allocated to each training job. Let's set our search parameters. You can set the amount of models that can train simultaneously, which is the parallel trainers. In this case, let's set 4. You can also set the amount of candidate models that will train before the search is completed. So let's also do 4. Let's also head to the advanced options tab to enable our feature engineering search. Let's also do 4 candidates and 4 trainers. And you could also customize your search much more. Let's say if your data set has a lot of features, you could allow Modela to automatically narrow down the amount of features. You could also generate baseline models for each algorithm with the default hyperparameters. If you have a binary classification data set, you could also enable automatic imbalance handling. We can also generate ensembles, voting ensembles, and stacking ensembles with the top models it generated, as well as interpretability visualizations using Shapley values, ice plots, line explainers, counterfactuals, early stopping, if for larger model searches, and these are not as important. So why don't we start our model search? And now what this is going to do is it's going to schedule a job on our cluster to split the data set into training and testing data sets. So if we go to our jobs tab, we can see the data set is created. Here is the job and its information. There's the pod, and this pod is running on our Kubernetes cluster right now. And now that the data set is split, it's going to begin the feature engineering search. And what it's going to do here is sample models with different feature engineering configurations, try different feature engineering settings across the possible search space. So let's see, like in this model, we have one hot encoding. Well, usually they would be different, but given enough models, it'll search the entire feature engineering search space and determine which feature engineering configuration is the best for your given data set. So, and we can also check out the model YAML that was generated by our cluster. So this was generated by the study controller, and it contains all of our hyperparameters, our feature engineering pipeline, and this is essentially a scikit-learn pipeline. And what this does, and since it was submitted, all of these jobs are running on our cluster. So you can see some of them have already finished training. And it seems there's only one more job left. And it should finish in just a second. Yeah. Should I mention, you can also query these models using kubectl, since this is a Kubernetes native system. So if this doesn't finish in just, okay. So now that the model search, the feature engineering search is completed, now it's going to start a search where it's going to try different algorithms and hyperparameters and tune the hyperparameters of algorithms it's already tried. So now it's sampling XGBoost models and LightGBM models, and given enough time, these models would train, but I don't want to keep you waiting. So we're going to just quickly head to an already completed version of this study. Yep, the study is already completed. In this study, it shows logistic regression. And if we go to the model spec, we can see the train confusion matrix as well as the test confusion matrix. All of our metrics that were computed during the test phase, our hyperparameters, our precision recall, ROC curve, and all of the visualizations it produced during the profiling phase. And now that this model is completed, it's been packaged into a container and is ready for deployment inside the predictor resource. And what this predictor resource does is it creates a Kubernetes deployment, which serves an API for your model and multiple models if need be, such that if you wanted to have shadow models or canary deployments. It also supports a lot of other MLOps features, including auto scaling, drift detection, prediction logging, and so on. So all we need to do to make predictions is go to our already created resource. Well, usually it's supposed to, well, usually it shows you the features, but we can also go to our data app to make a prediction, which is a Streamlit dashboard. Yep, just a second. Yep, and now our Streamlit dashboard is ready, and we can make predictions with all of our columns and their enums. And we can get a result, change the features around, we'll get different results. And you can share this dashboard with anyone, especially if you have a ingress controller. You can have a shareable links for this dashboard. So this pretty much covers the demo of the core resources, which we're going to show you today. But if you want to see the rest, I highly recommend that you download the system and try it yourself. So why don't I hand it back to Tomer? Tomer, unmute.
Unmute. You need to let me share.
Just talk on these slides.
Okay, so if you can see, we have the resulting system. So what we have is the end-to-end AutoML system, Kubernetes native. It's not only running on Kubernetes, it's running in Kubernetes. It's a no-code because the way it was designed, very cost-effective. You can run it on any hardware. You don't need to use, you're not tied to any cloud or anything, or you can run it on any managed Kubernetes. It's completely private, which is kind of important if you work in a financial institution, for example. You own your data set and models completely. There's no cloud involved. Modela is a standalone system. It's a single tool for all the MLOps flow, so you don't need to understand different tools or combine them together, integrate with them. It's a build on top of a very mature enterprise-ready open source like Kubernetes, scikit-learn, pandas, and it automates all the parts of the machine learning lifecycle. And of course, it's scalable and highly available. We have distributed training. Since it's built inside Kubernetes, it's using the Kubernetes high availability features, which are mature and tested. And out of the box, it integrates with all the Kubernetes ecosystem because it builds on CRD. So, for example, policy engines, RBAC, security storage, it's already integrated. Next slide. Okay.
Yeah. Okay. Why don't we just finish here?
Yeah. So
our recommendation: try out the Modela operator. It's available to install now. Join our Discord or Slack. And if you want to become a beta user, we would greatly appreciate it. And we're open for questions. Okay.
Yeah, thank you very much. That was a great demo, and we could hear you very well.
Great.
And thank you very much.
Cool. How do I turn this off? Wait, how do I stop screen sharing? Wait, hold on. I'm trying to figure out. Okay, there we go.
Okay.
So, does anyone have any questions? Yeah, Reese. And you tell us if you hear us. Try it.
Yeah, I can hear you.
Okay, thank you very much for the talk and the demonstration of the tool. So with the Modela tool set, I believe you mentioned that there